Shortly after I came to Berkeley, the laser industry started in Silicon Valley. I can remember the first time I saw a helium neon laser. It was set up in a double garage in Sunnyvale. A few years later, laser development had progressed to the carbon dioxide laser, a very high-power infrared source of radiation, coherent radiation. And one day I wanted to show that to a lecture in sophomore physics. I called up the people whom I knew at the company and said, how about bringing your CO2 laser and putting it on the lecture desk so we can see how it works and give the students a first-hand idea of the developments that are occurring in optics and spectroscopy and atomic physics. Well, the response was, I can't do that because it takes a whole truckload, literally, a truckload of equipment to go with it to make it operate, a complete gas pumping system, and on and on and on. So he said, if they want to come down to the plant and see it, that's fine, but we can't possibly bring it in for a lecture demonstration. In this laboratory, the CO2 laser laboratory, we will have one right on the desk in front of us operating. And it's rather exciting to me to see that we can still have some very fundamental optics principles illustrated, put your hands on them, make the changes, and see things either work or not work. Mostly not work until you have experience. Let me talk just a little bit about a laser, perhaps from a different point of view than you've thought about already. You've all done BSc, and do you remember when we had an amplifier, an op-amp it would be, but we'll do it a little differently. We'll put a signal in to an amplifier, and we get a signal out. And if we put the amplitudes of those signals out over in, this is the gain of the amplifier. And we wanted a high gain, or in the case of an op-amp, we wanted to modify that because it was unstable with its gain in the naked state. So we put a feedback loop on it. We took some of the signal out and put it back into the input. Now, in most cases with the op-amp, we wanted a linear amplifier, so that was negative feedback. It opposed whatever was done, so that we could get a linear response for a signal in to a signal out. But you may remember, later on in the course, with one of the chips, we put in positive feedback instead of negative feedback. And then this amplifier, instead of just amplifying the input signal, it began to run away or oscillate. And there was a natural resonant frequency to this. So then, with this positive feedback, the signal out has a resonant frequency. I'm going to call it nu zero. And we could get rid of the signal in because once the amplifier got started, it just kept going because of the positive feedback. And the signal built up and up and up and up until the specifications, the capabilities of the amplifier were exceeded and it couldn't go anymore. Essentially, it gets overloaded. Now, you also remember, although we didn't concentrate very much on it, that you have to put some power in. You don't get something for nothing. But when we put power in, we got a signal out with a frequency to it, and this power would be DC. In other words, we're transferring the power from something we have to something we want. And this is called an oscillator now in its present configuration. And we are very used to seeing electronic oscillators. I mean, I built these things in high school when I was interested in ham radio. And in those days, we didn't have many of the things that you have today. Crystals and things were not easily available. And we just built a power oscillator and used it just like this in the radio frequency range. The marvelous discovery of lasers was that we could take the same concept right over into the optical region of the spectrum and get an optical oscillator. And that's a laser. Let me show how we're going to do that with a little different drawing. We need first something that will produce optical frequencies, optical radiation. Well, you're all familiar with a neon discharge. You've seen those for years. You put electric frequency on them, and you have a tube and with neon in it, and you put an electric discharge on it, put an electrode here, and an electrode here, and some sort of an excitation. Here I'll just call it HV for high voltage. And we get a discharge filling the tube, and out comes optical radiation. How can we make that an amplifier? That's, of course, the very interesting part. And now let me look into neon from an atomic physics point of view and show how we can make it an amplifier. I'm going to be very restricted in what I say about it, but I'm going to start with a two-level system, E2 and E1. This will be the ground state. If I had a cold neon gas, it would just sit there in the ground state. If I put an electrical discharge on it, it's like putting the neon in a bottle and shaking it very hard and exciting it. And neon has hundreds and hundreds and hundreds of energy levels, and as they radiate, get excited and radiate energy, we get a lot of lines in the neon spectrum. But I'm only going to concentrate on this one and the excitation between these two levels. And in a normal state, you remember that if I have N1 atoms here and N2 atoms here, N2 over N1 is proportional to E to the minus E2 minus E1 over KT, the Boltzmann distribution. In other words, it's the difference in energy divided by KT, where that's some effective temperature of the gas in the bottle that you're shaking. There are various ways to shake it, but this essentially is it. And now you can see that if this is on the order of 1 or 2 electron volts, and at room temperature, this is 1/40th of an electron volt, there aren't many atoms up here. What if we heated this thing up hotter than hell, as hot as hell? What if this went to infinity? These two would be equal. So the best we can do is make these two populations equal. But now, is there such a thing as getting this hotter than hell, hotter than an infinite temperature? And the answer is yes, there is. It's a process of collisions, and in here we put a little helium, and if we put enough in there, we can end up that this no longer holds, and we can have N2 over N1 is greater than 1. There are more population here than here. That's one of the first discoveries in making a laser operate. I should mention to you that Einstein is the one who explained many, many things about this population, the equilibrium, this kind of a thing. And he introduced ideas which made the laser possible in the early part of this century. But it wasn't till the middle of the century that people were smart enough or had enough technology and engineering background to make it work. And I know because I was there and I saw one of the very first lasers demonstrated at a national meeting of the Optical Society. Well, now that we have N2 greater than N1, let's ask the question, what happens if we send in radiation here? And let's make this radiation H nu 0, where H nu 0 is E2 minus E1. Well, now you know from elementary physics that we could cause a transition from here up to here. But you will notice that since now I have N2 greater than N1, we can also cause transitions downward. And because N2 is greater than N1, I can cause more transitions downward from this collection of atoms than I can transfer upward. And the marvelous thing about it is that each of these that comes out now has the same frequency, and each is H nu 0. And I now have one photon going in, more coming out. They are not only the same energy, but the phases are exactly the same. That's called coherence. It is stimulated emission. And now you see we get more out than we put in. What's that but an oscillator? Now clearly, we don't get something for nothing. We're putting power in to this high voltage and the current that flows from the power supply. We're not getting nothing. We're not getting something for nothing. So now, if I take this in this condition and I put in one photon like this, h nu 0, I am going to get a lot out of the other end. And so I have amplified this signal to make this signal. But it doesn't oscillate yet any more than our electronic one did, our op-amp. We need to get some feedback. So we need to take a portion of this back and stick it back through here, bleed it back through so that we can get a self-sustaining thing and build up and build up and build up until the system is overloaded. Now, in the electronic case, it was easy. We just put a wire from here to here with the proper circuit elements to make it in phase. We can't do that here, and so we must use an optical trick to do that. And that optical trick is to put a mirror here, like that, so that the radiation, when it hits, turns around and comes back through, like that. So it sweeps a second time. But now it produces more stimulated emission, so each of these produces many more. It's a cascade. They come streaking back through here and go out the other end. So I will frustrate that, and I will put another mirror right back here. So when they get here, they turn around. So the radiation sweeps back and forth like this inside of this cavity. Just for to be the same, I'll put this mirror out here. So we now have a cavity, and the radiation is going back and forth. Well, you might guess that if I don't have the cavity just the right length, when light comes and is reflected and meets that coming this way, we won't get coherence. They won't be the same phase. So we must adjust this length so we get standing waves of radiation inside. That's just like a string and resonance. So now there is a resonant frequency. The atom has a resonant frequency. We adjust the cavity length so it has the same resonant frequency. And we put the mirrors, and it goes back and forth, and now we have an oscillator, just like in our electronic case, except now it is light. Now, even more than that, we have to have some other considerations that the electronic industry solved long ago, but the optics industry took a while to do it. There are always some losses in here, and we have to compensate for those. We have to have a gain in this amplifier greater than the loss. And in early days, this was extremely difficult. When I first went to this garage in Sunnyvale to see the helium neon laser, if you had so much as a speck of dust on this mirror to scatter the light, it would quit lasing. The gain was so crucial. It was just a fraction of a percent over 1. And a little speck of dust in this region would make the laser flicker, so it had to be totally enclosed. Well, one of the reasons for that, let me erase these now since we understand the radiation is there. The end of this tube is really a window, isn't it? Because you have to enclose the gas at some pressure and have this discharge. But at each face of a glass window, the absorption is the scattering of light is about 4%. So each of these we throw away for 4% of the light, and we can't do that, and therefore the losses in that case exceed the gain. So we have to change that, and do you remember from elementary physics that if we have a piece of material like glass at an angle called Brewster's angle, that one of the polarizations will go right through with no losses? That's a Brewster angle window. So one polarization, the one in the plane of the chalkboard, will go right through here and go back and forth, and we'll put another one on the other end here. like this. And now we have reduced the reflection losses essentially to zero, and we can have the gain greater than the loss, and here is our light oscillator. And the acronym LASER, which is written, is light amplification and stimulated emission of radiation. That's exactly what we are doing here. So far, I have an instrument here with radiation going back and forth, and it is an oscillator, but we haven't done anything with the light. It's all contained in this cavity between the two mirrors. So you might ask, how do you couple radiation out? We'll go back to your electronics. What do? You connect a wire with a RC network or something to take some of the energy out. If you take too much out, it will stop oscillating. In our particular case, instead of making this a totally reflecting mirror, we make this partially reflecting. As much as several percent can be transmitted, and so our radiation now, most of it goes back in, but some actually goes through. And then we couple and do anything we like with this output radiation. We can look at it and measure it for the properties that we're interested in. Then, I've really just left this as helium neon, but ours is not helium neon, it is a carbon dioxide laser. So the gas in here is carbon dioxide instead of helium and neon. And it has some other gases in it. I won't mention those now because they're fully described in the write-up. But the essential part is carbon dioxide. The second thing about it is that we have many more energy levels than this. And we get many more possible frequencies out depending upon how we adjust the mirrors here and what cavity length makes the various frequencies resonate, because the length of the cavity and the resonant frequencies then are very important. And we have other sets of levels that are different than this, and they are in the infrared instead of in the red as they are for helium neon. So you cannot see this radiation, so pay attention. It doesn't hurt to look into the helium neon lasers that we have in the laboratory because they're red and you can see it and you realize it instantly and move out. CO2, you can't see it. And it is very, very, very much more powerful. And therefore you don't dare go look in it with your naked eyeball. You need to be very careful of that. Now, a couple of other things are of interest here. One simply is that this gas mixture is very crucial because you need to make this population larger than this population. And if you don't get the mixture quite right, it will quit on you. Many times people get very frustrated after the alignment of it and give up, whereas it's really the gas has problems. It is not the right mixture, it has impurities, and it won't work. That's something we will leave for discussion when we go to the equipment. Now, since I've said that we get other frequencies here, let me just say we get one H nu 0, but we get nu 1, nu 2, and we get a number of them. Is there any way that we can select one of these and get just one at a time out of the laser? Well, stop and think a minute. I have two reflecting mirrors here. This one's partially transmitting, but I have two reflecting mirrors, and they reflect any wavelength. What would happen if instead I put a diffraction grating in place of this mirror? And I'll draw it the other way just to emphasize it's different. Suppose I put a diffraction grating here. You remember the properties of a diffraction grating? It produces various orders that get reflected or diffracted. And the order depends upon the wavelength. The crude equation we use here is just m lambda is 2d sine theta, if you want to refer back to your elementary textbook about that. And whatever angle we have here of changing the grating, we can then change the wavelength that's reflected back. So certain wavelengths and certain frequencies will be reflected back one by one as we rotate the grating. So part of this experiment is, after we've got it working and we know we can cope with the experiment, to put in a grating and scan with the grating. And then we can produce whatever frequency we like of these that are permitted by the CO2 molecule and the energy levels that are populated. Now, after that, the other things we have to remember simply is that we don't get something for nothing, as I mentioned. There's power going into this all the time. There's high voltage on the tube. We are pumping up the upper level with our electronic discharge in order to get the coherent radiation that comes out. The total process is inefficient, and we are trading just raw energy for something very directed in coherent radiation in the infrared. And I'll close this part of it with simply telling you what it was like at the first Optical Society meeting in Palo Alto when a CO2 laser was on display. It was put there by one of the very prominent companies now, and the safety regulations in that day were absolutely zero. Here was the CO2 laser sitting on the desk. The representative, a first-class physicist of the company, had a champagne glass in his hand. And you looked at the laser, and it was in the infrared, and so you couldn't see anything. He would put up the champagne glass, and within seconds, 1 or 2 seconds, the champagne glass would be shattered in his hand from overheating of a spot on the glass. And he would do that repeatedly while people like me were standing around watching with naked eyes, and we could easily have seen the radiation coming off of that champagne glass and suffered some permanent damage. Well, those days are gone forever, but remember, this is really a spectacular energy source and can produce effects such as shattering the champagne glass or burning a fire brick. So be careful. And we will now go look at the equipment. This is the CO2 laser. The cavity itself is contained between this front mirror, which is the output mirror, and the rear mirror, which is back here. And it's contained in this region with the associated discharge tube vacuum and all the other elements, which we will talk about shortly. In order to make the laser operate, we have to have the light going straight down the center of the bore and have the end mirrors operate parallel. To do that, we need a helium neon laser as a center line because its light just goes straight. So we have a helium neon laser right here, which comes out to 2 mirrors to make it turn the corner and go down the bore of the tube. And we align it by watching the dots where the helium neon laser light goes through various windows or mirrors. In order to see the dots better, we need to turn down the light some. First, we have to get the alignment light going straight down the center of the bore before we can adjust the end mirrors. And to do that, we have to adjust these mirrors here, which send the light down. We can tell if it's aligned down the center by looking at reflections from the side walls of the tube. If the light's going straight down, we shouldn't see anything in the center of the laser tube. If it's hitting the side, we know we're not yet in alignment. If you'll turn out the lights now, we can look and see what the light is doing. And you can see it goes almost all the way down to here. The light is just skipping along the walls of the tubes. And if I make a slight adjustment on the alignment laser, you can see how the light then goes down the center, hits the sides, changes, and it takes a lot of care to get it just the way it ought to be so you don't see anything down the whole length. In addition, it has to be centered, and that requires looking at the end windows now. And let's move back to the other side now and look from another angle at these end mirrors, and I'll show you some more about the alignment. Now let's look at that, as we said, from the other side. Would you turn on the lights, please? This is the other view of the output mirror, and I'm going to adjust the direction the beam takes with this mirror on the outside. And if we look a little closer, you can say that this is the output mirror and you can see the spot in it. Then it has to go into the discharge tube itself, and here's the Brewster angle window that I spoke about earlier. And it's at the polarizing angle, so only one polarization of light goes through without diminution. And we want this spot of light to be in the center of both of these, and we have the outside adjustments to do that. And you can see, as I turn this mirror back and forth, you can see how the spot goes back and forth. And the aim is to get it in the center of both and going straight down the bore. And of course we have to use the back mirror, the rear mirror, to come back up through the bore along the same path. Now let's just speak of a couple of other things as we go down the tube so you'll see what they are. First of all, we have a little housing around this Brewster angle window and a heater inside to keep it warm, because it's a salt crystal and it's hygroscopic and we don't want it to melt away on us or even to get cloudy. Then we have a gas pumping and filling system next to it, and if you can see it, we have an inner bore in which has gas, an intermediate bore which is water cooling because a lot of power is being dissipated in there, and then an outer tube which is a gas reservoir to help keep the gas pure and clean during operation. Then as we travel down the tube, we have an electrode to put in the electricity to cause a discharge. We have another electrode in the center, which on this tube is not used, so we don't need to worry about that. And then we come back down the tube and you see it's symmetrical, the same sort of a gas handling system, an electrode, a Brewster angle window. Now, we also have the option in putting in, this is the back mirror here, which I spoke about. We have the option of putting in a diffraction grating when we want to fix a specified wavelength, because as you can see here, the diffraction grating fits right into place and acts as the end mirror in the cavity. And as we turn the diffraction grating slightly, we can tune which wavelength goes straight back down the bore. You'll also notice the cavity is a little shorter, but that has no practical effect on the laser as we are using it. Here's a view at the grating end of the laser, and you can see the end window with the light coming through. It's not centered and it doesn't look pretty, but we're just trying to illustrate it, so I'm not going to worry about that. I'll put instead in a piece of paper, a white piece of paper in here with a pinhole in it, to see if I can isolate a little portion of the beam so that we can then see the light reflected from the grating and how we change the wavelength. Now if you'll turn the lights out, then we can see the red spots from the grating. And you see those are orders of diffraction of the grating. And if I want to tune the laser, then I merely change the angle of the grating, and you can see the orders move until I get the proper wavelength going right back down the bore through that little pinhole. That's the way you change the wavelengths. Of course, the CO2 molecule has to have energy levels corresponding to it, and that takes a little care to get the grating oriented just properly. Now we're ready to see if our alignment has been correct and if the laser will actually work. But before we do that, we need to take some safety precautions. We'll return to the business end of the laser, and first of all, we want to put on the safety glasses, which you'll find in the corner of the room. They cut down the infrared light enough so that if you should inadvertently see the beam or a reflected part of it, your eyes will not be damaged. Then we need to put a fire brick in front of the laser beam in case we inadvertently forget to put something else there or it just goes unprotected. And then we want to move in place a power meter like this in front of the laser itself. So now we need to see if it works, and we do that by starting the electric discharge in the tube because we have it all filled with gas, and let's see how it goes. So we need to turn on the power supply and go with the discharge. The high voltage is on. We'll press the igniter button and the discharge will start. And we can't really see it with the lights on, so let's turn off the lights so we can see the discharge. Now that's the way it's going to look whether or not the laser is actually operating with output power. There's no way you can tell by looking at this discharge. In order to tell if we have any lasing action, we have to put the power meter in. So let's turn on the lights again. And I have a power meter, which I will just adjust here to be exactly in front, and perhaps tweak the mirrors just a little bit. And we look at our power meter, and there we are with 400 milliwatts of power. And as you look at this, it happens to be very stable now. The needle will often oscillate. But you're in business, and now you can go ahead and make all the measurements you need on the CO2 laser.